And I worked 17 years as a practitioner in an area in Norway, in mid part of Norway, with mainly dairy cows. Quite different conditions from New Zealand, smaller herds, in-house in the winter season. We have a long winter in Norway, but also some similarities, so not so different. Almost all of the cows in Norway are Norwegian Red cows. About 85–86% of them are Norwegian Reds. So that's what I know. That's what kind of my experience is built on. I worked 4 years for Tine, the national dairy company in Norway, as a animal health advisor, and I started in Geno back in 2017 and in Geno Global in 2021. So that's roughly my background for this. I'm going to open the show, and Joshua Hoffman from USA will have the last session talking about his experience from running a big operation in USA with mainly Norwegian crosses as the breed of choice also there. I will talk a little bit about Geno. I will talk about the Norwegian Red dairy cow, tell you a little bit about Geno's breeding program, what genetic gain we get, and what levels of genomic accuracy we have. And I will also talk a little bit about genotyping and the use of RedX, which is our sexed product that we can offer. And I will also show you some data from Ireland, which is quite comparable to the New Zealand conditions. They are also mainly grazing-based. So we have some good data from there. The genetic gain, genomic accuracy, and genotyping is a little bit technical, so bear over with me if it's complicated. But I very welcome comments, questions, discussions from the audience. So I hope we can have a exchange of experience there, so also I can learn a little bit and make a better choice of Norwegian Red Bulls for you in the coming season. So be active and ask questions if you don't understand or you want to comment anything. Geno is located in Norway. Norway is up here and New Zealand is down here. So it's as opposite as it can be. Also, when you have winter, we have summer. When you have day, we have night. And your most important export product is dairy products, while our most important export product is oil. So it's a little bit different. Only 3% of this country is arable land. 97% is mountains, forests, and swamps, not possible to run agriculture on. So we are we need to use our resources very well. And that reflects in the Norwegian Red breeds. They need to be able to utilize these resources and produce high quality protein and fat sources for human consumption. So that's what we are aiming for. Geno is a breeding cooperative, and all of the farmers in Norway are owners of Geno. So if you have a dairy cow, you also are an owner of Geno, whether you want or not. You can kind of go in a separate direction, but most of them are members in Geno. About 7,000 dairy producers in Norway. We have much smaller herds than you have here, but we are also kind of grazing-based or graze-based, because graze is the most important resource we have, either like grazing in the summertime or like graze silage in the wintertime. In addition, we operate in 30 markets worldwide, most of the European countries, Americas, Asia, New Zealand, and Australia. We are also operating in China, so we are all over the globe now. This is our facilities. We are located in Hamar, about 1.5 to 2 hours drive from Oslo, the capital. And we have departments in Trondheim. This is the area where I come from, and also in southwest in Stavanger here. That's mainly for distribution of semen. We have our testing station at Øyer, our main office at Hamar, and our bull station at Stange. This is not far away from each other. We also have an R&D department at Ås, which is where the University of Life Science is located in Norway. And some of our employees are 50% Geno employees and 50% professors at the university. So that's where our R&D department are. This is how it looks. This is just a dairy farm, used to be, that we bought back in 1976, and in the old barn here now we have our production facilities. The conventional semen is here and the Red X production is over here. The main house is mainly used for representation. This is where we keep our bulls, and you can see the farm over here. So this is a little bit away from the farm, where we have our barns for bull housing. The big lake in the background here is Mjøsa, and that's the largest freshwater lake in Norway. Good area for agriculture, one of the best in Norway, so we are located in a good place. We grow our own crops to feed the bulls, and we also have some forest that we run, and also some cereal production. This is our newest barn that we started to use in January this year, so we are very proud of it. And this is how it looks inside, where all of the bulls have single pens, and we have emphasized the animal welfare in our new barn there. So this is roughly how we operate in Geno. About the Norwegian Red breed, this is how they look. It's a medium-sized dairy cow. We are world leading in fertility. They have good solid production. And they are feed efficient because of the slightly smaller size compared to other breeds. They are made to fit the Norwegian farmers as best as possible, and they have always emphasized kind of the ability to utilize the resources, the scarce resources we have in Norway about grazing. So that's the main purpose of them. They also have some beef abilities, as it is a dual-purpose cow. And for an average Norwegian farmer that fatten his bull calves, 25% of the income will come from the beef side of the Norwegian Red genetics. For that 25%, about 60% will come from the beef bull calves, and 40% will come from the female side of it. The carcass value of the dairy cows when they are done milking is high, and also some are producing beef on heifers. Because that's a good economy in Norway. So that's kind of a side effect. Maybe not so relevant for New Zealand at the moment, but we see the development in, for example, USA, where they now have learned to appreciate the beef side of the Norwegian Red. And they get, how much is this, Josh? $200 extra? $620 for a, yeah. But you need a market. You need someone that is willing to pay that for them before it's relevant for New Zealand. But be aware of also the beef side of it. And I also think the beef side of it, the more massive body, it's part of what makes them robust, good health, and also to keep their condition. And that's the key word to keep the high fertility as high as it is. Grazing outside in the summer, we try to graze as much as possible because that's the cheapest way of producing milk. The shortest up in north, they can graze for about 3 months. Down in southwest, they can graze for about 5 months. The rest of the year, we need to house them because it's all covered in snow. Population average. When we're talking about population average in Norway, it's important to be aware that in Norway we have a quota system. So the farmers are not allowed to produce as much milk as they want. We also have a good animal recording system, including 98% of the herds in Norway, and they need to do to keep records and do farm tests at least 6 times a year. If they don't do, they get the penalization in the milk price. So that's the main motivation to do all of this work. We also get data from Tine, the dairy company, which is owned by the same 7,000 farmers that owns us, and also from the slaughterhouses, which is also owned by these same farmers. So the flow of information runs freely between all of these institutions. And that's kind of our gold treasure, that we have this really, really good phenotype registration system that makes it possible for us to run our breeding program with a high amount of accuracy. You find about the same in some of the other Nordic countries, but not at the same level as in Norway. So that's also important to be aware of. And since we are keeping records, getting records from 98% of the herds, that will include both the very best of the farmers, but also the not so good farmers. So be aware of that when we are talking of average results here. But in spite of that, we have an average calving interval of 376 days, 1.6 inseminations per pregnancy in average for all of the farmers in all of the country. Non-return rate 56 days on 73.9. Somatic cell score on 113,000. In Norway, you get penalized if you're over 200,000 in somatic cell score. So that's what all are aiming for. Below that, it doesn't really matter. A little bit higher risk of mastitis if you have a higher somatic cell count, but most of them live good with the average here. But you can find good farmers that have an average somatic cell score below 50,000, and you can find farmers that have 1.0 or 1.1 inseminations per pregnancy year after year after year if they do their work well. Cows not treated for clinical mastitis, 87.8. Cows not treated for ketosis, 98.9. We don't see any ketosis longer. So being a vet in Norway is really a hard time. You have nothing to do, and that's why I'm here. Cows not treated for milk fever, 96.1. Stillbirth rate as first calving, 3.8%. So this is the numbers that including 98% of the farmers in Norway. The diet is mainly grass-based, individual feeding of concentrate to each cow based on milk yield. We don't grow alfalfa or maize silage in Norway, and we usually don't import feedstuff, not more than necessary. We import a little bit of soya for our concentrate, but we try to be as self-sufficient as possible and then utilize our grazing resources. That's what we are aiming for. In average, 31 kilos of concentrate per 100 kilos of energy-corrected milk. That's the average numbers. Most of it is used in the wintertime when we have silage at slightly lesser quality than fresh grass, of course. We also have this habit of mountain farming. I don't know if you have heard about this, but in summertime, all of the cows, or mostly all of the cows, are moved up from the valleys where they are in the wintertime and up in the mountain areas. And these are quite as you operate all the year in New Zealand. There's a milking parallel central, and they are grazing around on the different pastures here. Usually these are owned by a cooperation of farmers, so maybe 5 to 10 to 15 farmers own one of these mountain farming setups together. So then they move all of the cows up there, and they can be 100, 150, 200 cows running here grazing. And this is also because then they can hire some youth to be up there milking, and they have time to do the cuts and secure the harvest for the silage for the winter. So this is a very usual setup. Some are also letting the cows just outside the fence, so they go into the wilderness and graze, and they can produce a lot of milk by doing it that way also. This means that the Norwegian Reds need to have good feet and legs. They need to be able to walk. Nowadays, they drive them up the hills, but in the old days, they used to just move them by walking. And the longest distance they moved them was 2 days. And then they spent the night together with the cows up in the mountains. Really, really nice, if it's good weather, not if it's raining. And then they kept on walking the next day. So this is a little bit back in time, but we still have these mountain farming systems that are pretty much like you have in New Zealand today. Any questions, comments to the Norwegian Red, to Geno? Yeah?
Well, what were the origins of the breed? Was it a composite breed, or where did the original genetics come from 100 years ago or whatever?
Good question. Next slide. Back in 1935, the Norwegian Red was established. And that was established by some progressive farmers. Before 1935, we had what was called Lamarckism. We had one breed for every valley and every fjord in Norway. And they were specific to that area. And they really varied a lot, both in size and looks. Some of them were black and white, some of them were red, some of them were brindle or tiger striped, some of them were polled. But we weren't able to do any good breeding on all of these different groups because they were so small and we couldn't get any genetic gain breeding by them. So in 1935, some progressive farmers put their heads together and decided, no, we are going to pick the best animals from all of these breeds and make a Norwegian breed, and we call it the Norwegian Red cow. That's what was they did. They also imported some Finnish Ayrshire to better the genetics. Back in the 1960s and the 1970s, we also imported some Holstein Friesians to better the volume. So we have kind of picked the best genetics where we could find them and put them into our breed to make it as practical and as economical as possible after the wish of the Norwegian farmer. So that's how it started. Then we have introduced artificial insemination, progeny testing. We run progeny testing for many, many years. I'm not going to go through all of these, but in 2016 we had a full transition to genomic selection of bulls. That's pretty late compared to many of the other breeding companies, but we wanted to be sure that we have enough phenotypes to be able to have a high accuracy on our genomic selection. Because genomic selection need phenotypes. You need to correct the genomics with good phenotype records. Otherwise, you don't know where you're going. So that's why we waited so long before we introduced genomic testing in our breeding program. 2018, RedX, sexed semen, where we were able to make the next generation of the dairy cows for the farms from the best cows in the herd. We also started our embryo production program in 2018, and the two biggest research areas we have now is methane emission recording, where we have these sniffers record from about 1,000 cows every year. So the goal is to find to introduce also a methane emission trait for the bulls. So then you can pick, will you have a bull that gives daughter with high methane emission or low methane emission? This, of course, need to be balanced with the production traits and everything else that we are also breeding for. And we are also, in the same farms, we have these throts with weights, so we can weigh up on per gram how much roughage they get. And these herds are commercial dairy herds, so we just rent our place into these farmers, and they have all robots, so we can get all of the information from the robot and puzzle this together into our breeding program. So that's what we are mostly doing now. This is how it works. 200,000 cows in the breeding nucleus. That's about all of the cows in Norway. You have 5 million cows, so we are a little bit behind, but doing our best. Gives about 100,000 bull calves, 100,000 heifer calves. We select 8,000 of these 100,000 bull calves based on pedigree. So we go for the ones that we know have high merit parents. And then we send out the testing kit, genomic testing kit, to those farmers when the calves are about 1 week old. And then we get back the answer when the calves are about 3 weeks old. Then we select the 150 best based on their genotypes and buy them into our testing station at Øyer. And we keep them there till they are 12 months or roughly around 12 months till they start producing semen, till they are sexually mature. And then we collect 50 of the best of these 150 every year. That becomes included in our elite bull program. So that's the bulls you have to have the ability to choose among. That gives us a selection intensity of 0.05%. So if we are doing this right, which we think we are, you can select from the 0.05% best bulls in the Norwegian Red herd. We have the same run on the female side, 100,000 heifers, a little bit more genotype, because many of the farmers also genotype all of their females in the herd, because they want to know. They want to know who is the best cow, who am I going to recruit from. And they want to know the genomics behind it, not only the phenotypes. Buy in about 120 heifers, and then we produce about 4,000 embryos. Use both techniques, both flushing and IVP or OPU IVP selection. And that makes it possible for us to combine the very best females with the very best males, and they will then be a bigger and bigger proportion of our elite bulls that we can present. We see them already. All of the Norwegian bulls that have ET behind their name is from embryo transfer systems. This is mainly because the use of RedX or sexed semen has become more and more usual in Norway, and they always use the red eggs on the best females. That means we miss out on the bull calves from the best females. So that's why we needed to go into embryo production to compensate for the use of red eggs. So that's the logic behind it. This is where we are heading. This is the weighting in the total merit index, which we use to kind of rank the bulls in between each others. The highest trait now is udder confirmation with 27%. The next highest is milk production index with 23%. We change these a little bit each year. We can't go really in different direction because breeding cattle is a slow process. But we try to pick up the trait, what is moving in the industry and what is more important now. And we felt that we were lacking behind on udder confirmation, so that's why we put more weight on that. And we already see the result of that. These traits also have sub-traits, so we are not breeding for udder confirmation as a whole. We also breed for fore-udder attachment, rear-udder attachment, rear-udder height, rear-udder width, teeth length, teeth thickness, and central ligament, 8 subtraits under the udder confirmation trait. And we have also changed a little bit the weighting within these subtraits to be sure that we are doing the best. We found out that we had a little bit too high weight on central ligament, and if you weight central ligament too high, it tends to draw the teeth towards each other, so they will be really, really tight. So we have, and it's not a good correlation between central ligament and longevity. The highest correlation is between fore-udder attachment and rear-udder attachment and longevity. And that tells us that these are the traits that are most important for the cow to be able to have a good udder for a long time and last for a long time in the herds. So that's why we have put a little bit more weighting on those traits now than we had before.
What's your focus on the milk production index?
The payment system in Norway is mainly per solids. You need to reach a certain level. If you don't reach that level, you get penalized for every kind of 0.1% point that you are below. So, and also on the opposite, if you produce more solids than this kind of level, then you get a premium for that. And we also penalize a little bit for volume because we don't want to transport too much water in Norway. It's a long country, 1.5 times longer than New Zealand, so the transportation costs are really high. So it's a combination of weighting on solids and volume. What's also make it good is that here in New Zealand you can have the chance of selecting only the proportion of the Norwegian Red Bulls that are high on solids, or solid percentages, because I know that's what you are mostly looking for. So you don't need to kind of relate to all of the Norwegian Red Bull population. You can select the type that fits your production system the best. Just to give an example of what you can do if you have a large quota and a small barn, because then you are able to produce more like the genetic potential of the Norwegian Red. So this is an example from Timpelen Farm, which is located in the southwest part of Norway, where they graze for about 5 months. He is doing 12,500 kilos of energy-corrected milk with 4.58% fat and 3.78% protein. Calving interval is 11.6 months, and he has a somatic cell count of 97,000. Used 22 kilos of concentrate per 100 kilos of energy-corrected milk. Just to give you an idea on how this is run. The solid percentages here are also highly affected by how he manages it and how he feeds these cows. Any questions to the breeding program?
Just one small one was, have you, it's only been going a short while, but with your methane as opposed to efficiency, have you found any correlations with the methane?
We are in the start of this process. So what we have found now is that there are individual differences. Some cows emit more methane, nevertheless how you feed them, and some cows emit less methane. however you feed them. And this trait is heritable. It has a heritability of about 0.2 or 20%. We think that methane is energy on the wrong place. Instead of emitting it out to the air, it's better for the cow if she can kind of put it into her body and produce milk or solids from that energy. So that's the hypothesis, but we haven't enough data yet to say for sure. But this is something that we are really curious to find out and really longing to know, because we think that there will be a correlation between the low methane emissions and the high feed efficiency and the high production animals.
But not shown up yet.
No, we don't know. So it's a big question mark.
Thank you.
I'll come back next year and tell you.
Excellent. We'll be watching.
Other questions? Good, then I go a little bit further. Either I'm good at explanation or I have lost you totally. I don't know. That's good. This is the genetic progress that we have had in the Norwegian Red the last years, from 2000 to 2023. And in the years with progeny testing from 2001 to about 2011, we had a genetic gain of about 1.5 index point per year. And then we are talking about total merit index, which kind of sum up the weighting of the quality of these animals. We partly introduced genomic testing from 2012 to 2016, 2 index points per year. We fully went over to genomic testing from 2016, raised the genetic gain to 3 index points per year. And from 2019 to 2022, we used more red eggs and started our embryo production, raised to 4 index points per year. And now when we have a bigger embryo project and a lot more of farmers using red eggs, kind of they get the next generation of dairy cows from the best genomic cows that they have on the farm. We have a genetic progress of about 6 index points per year. That means half a standard deviation. Standard deviation is 12 in this TMR system, and we are, to be honest, we are really, really proud of this. There's not many breeding companies that have the same genetic progress per year as we have. And to use an example for milk yield, these are phenotypes from 98% of the herds in Norway. We have a genetic gain of 90 kilo per year. So 3 years equals 270 kilos more milk for the average farmer in Norway. That's the kind of the muscles that we can put into our breeding program. And this makes it possible for us to go in the direction we want quicker than we did before. And what direction we want to go is the weighting of the traits, and that is decided by the Norwegian farmers. So that's how this works. We have about now 220,000 genotyped animals, and we use all of the cows in Norway, 200,000 cows, as the breeding nucleus to do this. So we are really proud of the size of our engine.
Sorry, excuse me, just
Yep.
go back. Have you worked out on the top point, is it size of the animal, efficiency of the animal, or the amount it can eat in a 24-hour period? Is any of those three significant? Like, where's the gain coming from?
This is for the TMI, and the TMI then include these traits that I showed you, the same weighting on it. So we can go down to single traits and see how much will this kind of affect every single trait. And you can find it on norwegianred.com. There we have an explanation where we say where is the herd level and what is one standard deviation in phenotypes. So then you can go in and see, for example, for protein percentage, where are we now and what can we expect from the next generation if the bull you choose is one standard deviation above the herd or the population average. So it will be too complicated to answer all of those.
So that obviously leads into the BW system in New Zealand. Will the top ones of that, have quite a good BW when they transfer across to New Zealand BW system, or? How does that transfer to BW?
Very good question. I'll come back to it later, but it's not a good relation between the young genomic bulls and the BWs. When they get daughter proven, especially if they have a good group of daughters in New Zealand, we see that they make a big jump. So generally speaking, I will say that the BW system underrates the young genomic bulls, Norwegian Red bulls here in New Zealand, and it's a little bit better when they get daughter proven. But when they get daughter proven, they are 3 years after. They lack 3 years of genetic development, genetic gain. I'll come back to that. I don't know, was that the answer on your question? This is the genetic progress for some of the central traits, and you see the milk trait, the blue one, is the one where we have had the greatest development from 2010 to 2023, October and January. The second biggest one is udder exterior, the lighter blue one. So the weighting in our breeding program reflects in how this actually develop out in the herds when we look at the genetic trend of the animals. Fertility has also had a positive development, but to be honest, when we choose bulls for New Zealand, we generally don't look at fertility at all, because even the baddest fertility bull in Norway will add better fertility to most of the herds here in New Zealand. So that's not very important, but we have had a development there. The one that we haven't had a big development on is meat. You see the red one here is pretty straight. We haven't lost anything on the beef ability and quality, but we haven't emphasized that too much in our breeding system, because it's now more and more common to use red X on the best ones, best third, conventional on the mid third of the genomic animals, and beef on dairy on the lowest that you don't want to recruit for anyway. So the beef on dairy has in a way come instead of the beef abilities of the Norwegian Red. But we are trying to keep it as it is, because we know that the beefiness, it's what makes them more robust, more able to keep their condition, and gives these health traits and also fertility traits. So we don't want to lose that in the way. This is a purebred Norwegian Red side by Krovoll. We have had an increase in protein percentages from 3.25% in year 2000 up to 3.57% in 2022. And this is phenotypic trend. So this is how it really looks in the herds from 98% of the herds in Norway. This is highly dependent on how you feed the cows, and we know with the genetic gain we have now, this will continue to raise in a even steeper and steeper curve for the years to follow now. See the same on fat, and this is the top herds for Norwegian Red cows for solid percentages. So if you really go for it, if you really focus on it, it's possible to reach 5.41% for fat and 4.06% for protein, if you kind of manage it right and feed, and also choose the bulls that are high on percentages and do that for many, many generations. So this shows some of the potential that lies in it. While we have had focus on the production traits, we have managed to maintain the fertility. So this is also phenotypic records, non-return rate. That's how we measure the fertility. It's a little bit different. I don't know, maybe you relate more to daughter pregnancy rate or calving interval. It's many ways of measuring fertility, but non-return rate is the ones that are inseminated one time and don't return to insemination within 56 days after the first insemination. Generally, the Norwegian farmers don't do preg tests. They know that if they inseminate them and they don't see any more heat from them, they are generally pregnant. So that's why it's hard for us to get daughter pregnancy rate. Otherwise, we would have used that. For heifers, 76.8% in 2008, up to 76.9%, so pretty stable. For first lactators, 68.5% in 2001 and up to 72% in 2020. So there is where we have had the greatest gain in fertility. And the first calves are also the most complicated one, because they are the ones that are in the baddest kind of energy situation, because they have produced a calf, they have started milking, and they are still growing. So generally speaking, the first calves are the hardest one to get back in calf in Norway. I see some nodding heads also here, so that's also what you have experienced. This is the phenotypic trend for calving interval from 388 days for first lactators down to 374 days, 380 days for cows with more than one lactation, down to 369 for this group. Take-home message, the acceleration in genetic progress, especially in past few years due to right strategic decisions in our breeding program. We are proud of that. I won't hide that. We have full control. We know what's happening to each cow for 50 plus years. We have these records, and every time we run our breeding program, which we do every other week, we include all of the phenotypic data that we know about all of the cows in Norway that have lived in Norway since 1970 until this day. And all of the genomic information we have of the same cows. So we have a supercomputer that we use for this, and when we press enter, it takes 3 days before we get the answer, because it's a huge amount of information into this equation. But I think this is what makes our breeding program strong. The balanced breeding program and the comprehensive data collection paid off, and very high selection intensity, both males and females. You know the breeder's equation, where you have generation interval below the line. So we are now chasing generation interval. That will be the next thing that will bring us forward and bring the genetic gain even higher up. So we are now, before we were chasing years, now we are chasing months, and maybe in a couple of years we will be chasing weeks and days, because this is really, really important to get us as low as possible. That will speed up the genetic gain even more. This is also a Krovold daughter, I think. Any questions to our breeding program? Yes?
Since the introduction of the Redex in 2019, have you noticed any difference to your in-calf percentage? Like I find that the sex semen isn't as high in conception.
They have a little lower conception. I come back to that. I have a slide on that shows the difference between them. So keep that in mind till I come to that slide. Was it a no?
I was just going to comment on that. Like I've probably crossed 75,000, 80,000 breedings over the last 6 to 8 months. We're switching mainly to conventional, mainly to Red X, and just using a conventional bull as a cleanup bull, because we're not seeing the difference in things on the Red X. So it's right there with it.
What's your average age of your herd?
In average, we have 3.7 lactations. That's due to the beef ability, because in the old days, many of the Norwegian, or the habit was to inseminate all of the heifers, let them calve in, because when they moved from being a heifer to being a cow, they get a government support for each individual. So they try to let as many as possible calve in, and then they let them milk in the first lactation, and when they see that now we are reaching the quota, we can't produce any more milk, or now we need to move them into the barn, and we just have a certain amount of cubicles there, then they slaughter out the baddest ones.
So you can't get accurate data on the longevity of your milking herd?
No, not really, because this is highly biased of the political conditions and how they run this. So these will, of course, drag the average down. But we have data from the University of Michigan in USA, where they compared the percentage of the different breeds that were Holsteins and Jerseys and Norwegian Reds. And they saw for the first lactation, they were about even. For the second lactation, for the third lactation, for the fourth lactation, then they saw that the proportion of Norwegian Red was steadily rising towards the others, because they survived. So most of the culling in Norway is voluntary culling. It's not culled because they don't get back in calf or they get ill, so you need to get rid of them.
Well, that speaks for itself.
Yeah.
That accounts for the quarter of the, you said 25% of the income comes from beef.
Yeah.
That accounts for that.
Yeah, and that's the female side of it. So when they slaughter these first calvers, then they get a reasonable value for the carcass, plus that they get these premium from the government to make them cows, not heifers anymore. But it's a really complicated system in Norway, so I won't go into that.
It's a European for you. Swiss, need more than 2 cows because you get government subsidy. But could you tell me whether or not once a day milking, twice a day milking, how does that? Have you
Questions because we can't hear you.
Oh, just asking whether what in Norway, what's the once a day to twice a day milking regimes, which we're in New Zealand. We've got herds milking once a day, and most of them still milking twice a day, and it alters all these figures,
Yeah, I've never heard about once a day milking before I came here. So that's not a habit in Norway. That's not something we do. We kind of move in a different direction, because now we see that more and more of the dairies are moving from manual milking into robot herds. And these robotic herds, they milk in average maybe 3.5 times a day.
Yeah.
So we don't have any experience with that. But we have some experience from here in New Zealand that is doing that. And if you are look a little bit of leakage when you choose bulls, so they keep the milk in the udder and not leak it out on the grass. It looks like it functions also well here in New Zealand. I don't know if anyone here have experience with once a day milking and Norwegian Red. You have that?
Yeah, well, the udders definitely are holding up, but we're still quite young. We're about 4
The Reds,
year olds.
they look good.
Yeah, no, they're doing really well.
But it alters, I think it alters your fat figures, everything changes when you're once a day, you've got a difference. And the robustness of the 2-year-olds in particular.
Yeah.
Okay, so it alters a lot of figures, but if you...
Yeah, but we don't have any data from Norway on that, so then you need to ask Hamed and Craig here, and maybe they can look into it and see what they can find about it. So that could be interesting to do one time.
It'll take you some very good figures before you change these girls back twice a day, I promise you.
Yeah, that's good. We have to move on. Time is ticking. Genomic accuracy. This is a bit theoretical, but we'll take it step by step. How genomic selection work? You need a reference population when we know both genotype and phenotype, and then we can put it into this model where we take all of this into account, and then we can kind of choose select the candidate that has the genotype that we know is related to the phenotype. So to illustrate the genes of a dairy cow, they have about 3 billion steps in this double helix letter. They have about 3 billion steps. To illustrate that, you can picture in your mind a box that is 1 meter times 1 meter times 1 meter, 1 cubic meter. If you fill that box with books, it will be about 3 billion letters in that box. So that's the amount of information that is within every single cell in a cow. And if you open that box, pick up one book, open it on one side, take one word and alter one of the letters, then you can have a cow with double musculature. That's so small is a genomic change for the double musculature. So of these 3 billion steps, we look into about 55,000 of them. It's 0.017% of the genome, of the total genome of the cow. And how can we then say something specific on how will this cow be when we only look at this teeny tiny small proportion of genes in the cow? That's because most of the genes of the cow are similar for all cows. All cows have 4 feet. They have the head in the front, the tail in the back, and it's no variation. So it's not interesting to look at that. We need to look at the genes where there are variation. And we know where this variation is, and we know which letters will be in that particular step that is associated with, for example, high solid production. So that's kind of how this works, simply explained. The accuracy of this, how good we hit the right candidates, is really, really important on how good a genomic selection system works. And you see, when we started in 2017, even if we waited a little bit longer, we still had accuracies about 0.6 for kilos of milk and up to about 0.78 for fat percentage. But when we got more and more phenotypes over the years, in 2020 we are now up to a accuracy for protein percentage that is close to 0.9. And to compare it with a progeny testing system, this is about equal as for a bull with, for example, 80 daughters, where we know the phenotype of the milking of those daughters. So we are now up to the same level about as a progeny tested bulls with a small group of daughters. When you get a big group of daughters, for example 2,000 daughters, then you will experience accuracy of the selection that are between 0.9 and 1, maybe as high as 0.95. So this is about what we are talking about. But you can now compare our genomic selection system with a progeny testing system with a small group of daughters. Does that make sense? You follow me there? And this is, you asked this question about BW, because we see, no, not this one, it's the next one. This is the comparison of a genomic breeding value and a proven breeding value. So here you have the genomic breeding value in kilos of milk, and here you have the proven breeding value in kilos of the milk. So you can see this is the estimated breeding value, this is the true breeding value. And we have then taken the same bulls and see how they score when they were young genomic bulls and compare them 3 years later how they score when they are progeny tested bulls. Because we still do the progeny testing. We need that information to correct our genomic selection system to be sure that we really are selecting the right bulls. So you see that even the ones that, first you see this is the correction line, and you see that there is no bias in our genomic selection system because it's about the same amount of bulls that moves up that moves down. So that means that we are kind of hitting in the right direction. And some of them increase a lot, 258 kilos of milk for this bull from he was genomically testing till he is proven, and some of them go down. But even if you are unlucky and choose a young genomic bull that is among those who go the most down, he will be 3 years younger than the proven bull. And on those 3 years, the genetic gain equals 270 kilos of milk. So even if you are unlucky and choose one that goes a lot down, he will still be better than waiting for a daughter-proven bull. Does that make sense? Here is the BW. And you see here, I picked two bulls as an example. Ofstad, that now has a BW of 110. He was born in 2017, and he now has a TMI of about 7.8. Compared to Forin PP, which is one of our newest bulls, born in 2021, he now has a TMI on about 35. But he have a BW of 35 compared to BW of 110. But clearly Forin PP is a much better bull than Ofstad, that is older, because he has had this genetic gain for all these years from 2016 to 2021. So the BW doesn't reflect very well the true breeding value of the young genomic bulls. That's a challenge. That's something we are working with. But per today, it's not a good decision to look at the BW to choose young genomic bulls for choosing Norwegian Reds. Daughter-proven bulls have at least 3 years delay of genetic gain. 3 years of genetic gain equals 270 kilos of milk. Young genomic bulls will adjust every time new information is added. In average, half will increase, half will decrease. With accuracy of 0.9, even those who decrease the most will be better than an average daughter-proven bull. Questions? Comments? Do you believe me? That's good to know.
I only came for the beer.
Yeah. Sadly, you need to listen to this for the beer. A high cost. Genotyping and use of Red X. Why aren't all siblings like twins? Are they? Because for a calf, you say that he has the parental average, so all calves are twins. If you have the same dam and the same sire, they are regarded as twins, till you get some phenotypic data on them. It's a little bit theoretical, but bear over with me. All calves have a sire and a dam. That sire has a set of genes from his sire, and in this case, they are only positive genes. You know that in every cell we have a double set of genes. So we have two codes for eye color, and one of them is usually dominant and one is recessive, and that explains what is expressed in the individual. He also has a set of genes that he got from his dam. In this case, they are purely negative. The same with the dam, negative from the sire of the dam and positive from the dam of the dam. You follow me on this? Then we have this calf. Because when the body is making a semen cell or an egg cell, they can't go on with the double set. They need to choose just one of these, and they choose a little bit on each of what they have got from their parents. So in this case, the crossover happens here, and this is lucky because he got a big proportion of the positive genes from the sire of the sire, small proportion of the negative genes from the dam of the sire. From his mother's side, what's in the egg, the crossover happens here. A relatively small proportion of the negative genes from the sire of the dam, and a big proportion of the positive genes from the dam of the dam. This is a plus individual. He is really lucky. He's got the best from both sides. I have 4 children. I can assure you this turns out also in reality. I'm not going to tell about the sire and the dam here. This is called Mendelian sampling, and this is the true beauty of breeding. You can't control it. You don't know which combination will turn up, and this is also what is annoying about breeding. This calf here have a different proportion, a small amount of the positive genes, a big amount of the negative genes, a little bit more lucky on the dam side, a small amount on the negative genes here, a big amount on the positive genes. So this is a plus-minus individual. This is very simplified, but it's just to illustrate how it works. This is the parental average calf that have half of genes from both sides. No one are there. Most of the siblings share between 40 and 60% of the same genes. You can have siblings that don't share any of the same genes. They are not genetically related at all. That's 1 to 10 million. So it's really rare, but you can have it. Yeah, suppose that they have the same father and the same mother, of course. Genotyping of females, what's in it for me? This is kind of the value that we see in Norway. These numbers are not relevant for New Zealand, but I don't have enough knowledge to put up a calculation for New Zealand. But you see, in Norway, we say that genotyping all of the females in your herd makes a gross margin of plus minus 15,000 Norwegian crowns, which is about 2,000 New Zealand dollars, maybe, around there, 1 to 6, I think, per 2 to 3 lactations. So that's the value we see from genotyping the females in Norway. This is the relative conception rate for the Red X, 93.2% for all lactations and 98.2% for maiden heifers. This is a data set from Britain, where we have 8,000 insemination in this group and 4,000 inseminations in this group from many farms. So we kind of feel that this is true numbers. So it is a little difference, and it is also a little bit more tricky to use Red X. You need to be more thorough about the insemination timing of the insemination, but it's possible to get really, really good results also with red eggs. Some data from Ireland before we stop. This is a result from the Moore Park studies that was done in Ireland Research Centre, when they compared Norwegian Reds, Irish Holstein Friesians under grazing conditions and crosses of these two. So we see a number of first lactation cows in each group, a little bit higher on the Irish Holstein Friesian, average milk, higher on the Friesians, lower on the purebreds, and in between, but not a big difference from the crosses to the Irish. Average protein percentage, about the same. Average fat percentage, about the same. Average lactation mastitis incidences, lower on the purebred, in between on the crosses. But you see, the crosses tend to lean towards the best side of it. So that's the hybrid effect of this. Average first service conception rate, 59 compared to 58. 6-week in calf rate, 62, 72, 71.3. So you also see here they kind of lean towards the most positive side of it. Survival to third lactation, 67% here, 73 and 78% there. This says something about the longevity. So these are the data that we saw from these trials done by the Moore Park Research Centre. The economic results from the same results. Holstein Friesians came out third, the crosses on the best, and the purebred Norwegians in between. This is, of course, not relative for New Zealand, because this is Irish milk prices and Irish costs of feed and everything, but just as an illustration on how this works. Shane Fitzgerald, the significant factors include fertility, excellent mastitis control, low cell counts, and feed efficiency. In our three-way cross system, Norwegian Red has truly given us the strength and depth we aim for, crucial for optimal performance with the feed we provide. It's been key to our success. That's what he says. He has experienced in his herd. About 430 cows in milk, 6,000 kilos in average production, 4.3% fat and 3.7% protein. Here we have another one, Jamie and Stephanie Martin, a little bit higher production, 4.5% fat, 3.5% protein. And the key difference is in bringing the crosses into the herd has been that the herd is now easier to manage with less issues to troubleshoot on a daily basis. And that's the cow we all want, the cow that you don't notice, the cow that you don't need to pay extra attention to, that is there, is working, get back in calf, go out grazing, producing the milk. That's the most wanted cow for the Norwegian farmer, and probably also for the New Zealand farmer. Unless you like to trouble yourself with sick cows, I don't know. That's about all from my side. Thank you for your attention.